The MAINS project proposes subwavelength support for metro architectures which can facilitate the support of dynamic and high traffic volume demanding internet services like high-definition video streaming, social networking, 3D telepresence, peer-to-peer gaming, and cloud computing. Current video network solutions based on electronic packet switching, such as IP MPLS, VPLS or Ethernet, struggle to scale at very high traffic volumes. Furthermore, to support high bandwidth service demand, metro networks usually depend on real-time independent wavelength allocation without exploring individual wavelength sharing. MAINS proposes a new architectural approach which makes use of subwavelength by building an architecture based on dynamic time-shared use of single wavelengths using ultra-fast tunable components and time-shared optical network (TSN) systems. These will allow operators to offer different services or applications over independent subwavelength flows. A full wavelength, for example, may provide a 10 gig bandwidth, whereas in the MAINS architecture, 3 operators could be given access to 2G, 3G, and 5G subwavelength flows. To support this, a new approach to extend GMPLS control plane is proposed. Based on these, the MAINS architectures allow efficient deployment of distributed application services in a metro network offering advantageous support of dynamic high bandwidth demands for services. As a result, both CAPEX and OPEX are reduced, while enhanced capabilities for service deployment are achieved. This figure shows an overview of the network architecture proposed in MAINS. The network consists of 2 optical domains, which include the OPST Metro Ring network and the TSN Metro Mesh network. The MAINS project aims to demonstrate the transport and switching of subwavelength flows across the 2 networks administered by a common GMPLS control plane. A service request received by the GMPLS control plane will result in network control commands being sent to the OPST and TSN networks in order to configure the required subwavelength path across the network. In order to allow the 3 systems to interwork in configuring required subwavelength path across the network, the MAINS project proposes the implementation of an XML-based interface. The development of the GMPLS extension for subwavelength granularity, together with the XML interface for flexible cross-technology transport research configurations, provide a uniform way to describe TSN and OPST services to GMPLS-CP, and thus provide the platform to create seamless end-to-end services among OPST metro rings interconnected with TSN Metro Mesh. With regards to the ring and mesh metro networks, it has been proposed that 2 separate testbed environments will be used for verification and testing. The figure makes a distinction between the different functions and components by showing in blue what will be used in the first testbed scenario using the Essex Lab testbed together with the Janet Aurora research network, and in red the second scenario where PrimeTel's optical commercial network will be used. These 2 testbed environments are also used to verify parts of the proposed MAINS architecture in isolation and under different service loads to prove particular concepts related to traffic demand and adaptation of the architectural components to dynamic network changes. Several technical and logistical aspects have also been considered in choosing the 2 separate testbed networks. In the case of a telecom operator's network, the following considerations hold. A telecom operator can provide the operator's network with real customers and commercial OPST nodes. The ability to test and validate virtual PC services on subwavelength technologies in a commercial environment. The possibility of conducting surveys and performance tests with real users to extract results from the clients with regard to quality of service, quality of experience, using questionnaires or other means you might already use. Alternative topology setups can more easily be formed at an operator's network. However, testing in a real operator's network is more costly in terms of trial execution and requires dedicated resources for setup from a network, which may also be used for consumer services. On the other hand, using the University of Essex Janet Aurora testbed has been preferred for testing horizontal integration of OPST-TSIN and vertical integration of both transport solutions with extended GPLS CP to provide end-to-end services. To be used for demonstration of data plane OPST-TSIN interoperability, will be used for verification of the control plane extensions proposed within MAINS framework. To evaluate multi-technology interoperable GPLS CP, a dedicated testbed for optical network research is less costly for reproducing validation tests and provides a more flexible and less risky environment for repeating tests. The rest of the video shows the first field trial taking place between two sides of PrimeTel's network in Nicosia.
Here we have two of our nodes in the Nicosia site at PrimeTel installed. Firstly, we have the ring connections. So what we do is we go out on east and return on west. So these two nodes are interconnected back to back, and then we go out to a patch across the 5.5 kilometer span to the second site at PrimeTel, and then return again on the third node, node 3, here at the bottom. We also have two 10 gig XFPs used to connect from the optical switch to the N2 node for the clients. Transmit and receive. Here we just use our Ethernet ports for management, for the optical calibration initially, and to set up of the services for each client, and to monitor any alarms, traffic services, etc. Here we have two Netgear switches. You can't see it very well, but we have an output, the 10 gig output from SFP Plus to the client port on the Intune. And then what we have is, for each client, or for each MAC address, we have the 1 gig LAN Ethernet connections in inputs. As you can see here from the top, we then have server 1 and server 2. With their Ethernet ports connected for the two MAC addresses that Hami has set up for the clients, which runs to the switch. Okay, so here we have the 3-node ring, 3 beta Intune optical burst switches, all on a private LAN for management. What we have is a 5 kilometer span to PrimeTel's second site, with the third node at that site. Connected as clients on the client ports of node 1 and node 2, we have two switches on a 1 gig LAN to a 10 gig optical interface. Connected to those switches, we have two servers, 1 and 2. Here we just have a PC connected for management, which is what I'm showing it to you on at the moment. Later we'll show a client PC also connected to one of these switches, taking the information from both servers, transmit and receive from node 1 to node 3 and back to node 2 in a clockwise ring. So normally when we power up a new 3-node ring, we have to calibrate optically the power leveling So here you can see 3 nodes with their IP addresses for management, and the drop channel of each node, 17, 16, 19, with various different optical values for attenuation, any losses, insertion losses, and the gain for certain sections that we use optically on the nodes. We also use this for a bit error test, where we generate our own PRBS data for self-test of the ring before we put live traffic on. So it's kind of a commissioning setup. Basically, connect to the master node, put each node into service, which also have their own MAC IDs, along with the topology number. Each endpoint or each node has a set of MAC addresses for any clients that is connected to them. So here we have node 1 with 4 different MAC addresses. 2 of them are for the server, and 2 others for different client laptops. Node 2, we have no MAC addresses set up. There's no connections to it. Simply just a pass-through node. Node 3 has 2 MAC addresses from server 2. Each of these connections in default state would give you best effort traffic. But what we like to do is set up, for demo purposes, more realistic connections. So we've got virtual circuits here set up with 100 meg bandwidth at highest priority, from every source MAC to every destination MAC, to give you your optical ring connections. To create these services, you can see from node 1 to all other nodes, and node 3 we've created the same connections back to node 1. You can also see the source allocation bandwidth and the destination allocation bandwidth. So basically what class of service allocation you've created and what you still have available for each client or service.
This would be the first web page you see at the site when you connect to the service, the virtual machine service, which is basically what we're trying here. The service is running on the servers distributedly. Your virtual machine will be running on one of the servers, which is connected to each one of the nodes that Intune has provided. And basically, this would be the end user's welcome page. Once he gets here, he can deploy this message, and he could register here. I'm going to register Michael. But for purposes of, speed, I have already created my own user previously, which I'm going to log in with that. Once the user has logged in, this would be the basically the what he would see. He has a list of the virtual machines available. He can create at any time a new virtual machine by clicking here. Once he clicks here, this little menu deploys, and let's say we create a second virtual machine, Ubuntu, and we create the VM. Once we do that, we can see it takes a little bit of time. The server is basically creating that virtual machine for the user. So we can see now that the virtual machine has been created. Once the user if he would to fire up this virtual machine, he would basically go through the whole installation process of a regular machine. I've already done that, and we can see it now with Nicosia 1, which I have already installed. Let's start that up. So we activate the machine. And we can see that the operation has completed successfully. Now once we do this, we know that our virtual machine is running on our assigned server, which is research 2 at this IP address, 192.168.0.20, and we know that it's running on port 1025. We can also set an RDP password over here to secure our connection to the virtual machine. I have already done that. My password is my RDP pass. I can change it later for us to check that this is working, but this is fine right now. So once we know that the virtual machine is up and running, we know that it's on port 1025 like we just said. All we have to do is go to our remote desktop software. I am on Linux, so I'm going to use the GNOME RDP front end, which I have over here. And I have a session for exactly this port and this IP. When I click on it, it asks for my password. If I mistype it, which I'm going to do right here, it won't let me connect. You saw how it just flashed open and then closed down. Now I enter the right password, and hopefully we should be connected to our virtual machine, which is right here. And this would be basically a fully functional machine, 60 gigabytes, you know, just a virtual machine like anything you've seen, and you can connect with a remote desktop, you know, and play around with it, It's a full-blown system, really. It has everything you would really need. So let's say we want to shut the machine down. Well, we can do it two ways. We can do it the not preferable way, which is to basically come here and shut it down regularly. The system every 5 minutes is polling, so it will realize after a period of 5 minutes that the machine is down, and will update the database accordingly. But the proper way and preferred way is to just come here, select the virtual machine, change the state to shut down or pause, but shut down, and basically we click here to modify the VM state. We'll click on it, and the VM operation has been stopped, the machine has been stopped. We go check, and we see that in fact the window has closed because the RDP session has now been canceled because the VM is down. Now, one of the most interesting things in the scope of the MAINS project is the fact that we can actually move the machines around the different nodes. If we click here, we can see a map of Nicosia. If we zoom in, we can see that we have two sites. This is site 1, research 2, with this IP, which is where we were currently running. But we are here. This smiley guy over here is us, approximately. So we can select the IP of the node which is closest to us and assign the server. And by doing that, now when the user decides to start up that machine again, we will see that now it's a lengthier process because the entire virtual machine has to be moved from the original node, research 2, to the new node Research 3, and that is done using the Intune ring. So let's try that out. We click here, and now before the ongoing VM, like the VM operation warning was there for a few seconds. Now it's going to be there for approximately a minute. Anyway, this is now being copied to the remote server. The idea of this is that your average person can have use the same virtual machine at home or at work with a good quality of experience by having the virtual machine roam with him. See, now the VM operation has been completed. We have now transferred the entire virtual machine from one of the nodes to the other. As you see, now we are assigned to Research 3, which is 192.168.0.30. The virtual machine is in a started state, and again it's on port 1025. We go to this other session, which I had created previously, and we can now connect to that on the other server. And as you can see, we now have the virtual machine running just the same. Now, if we were to view a video right now, because we haven't changed location, we have moved the machine, but we are still in the same location. If we were to play a video here, I will provide a screen capture of that effect. It will be choppier because now it would be better because we are closer to the location of the node where the VM is executing, and therefore the latency would be shorter, smaller, and so the whole quality of experience would be a lot better. The video refresh, the interactivity, the mouse, everything would be better. When it's on the remote node, the actual information has to go all the way through the ring, adding about a 200 millisecond delay from what we have seen on the round trip time, and that is it pays its toll, on the quality of experience. So this is basically a quick demonstration of the service of the virtual machines, roaming virtual machines over Intune's ring topology, and we have fortunately gotten everything to work nicely. One thing, if you are running on a Windows system, it's a lot more, we could say, convenient to have one of these files that the actual system provides. It's an RDP file. You can download this to your computer and double click on it, and it already has the IP and the port into it, the actual username, and it will only ask for the password for you to type in. And that's about it. Let me just shut this down. We can delete the example virtual machine I created previously, and that's about it. Once the user is done, comes here and logs out.